In this video, we're going to solve combined loading problems. In the first problem, we have a wall and the load of 800 kilonewton is acting. As you see, it's not acting on the centroid. Well, it has distances from the y and x axis as given as x 0.25 and y 0.5. Well, the question is, determine the normal stresses at the corners A, B, C, and D. Let us calculate, well, the area of the section, the moment of inertia around the x-axis and around the y-axis. These are numerical values we need for calculation. Okay, let's try to determine what type of internal loads and moments are caused in this section A, B, C, D due to this 800 kilonewton force. We see that this force is not acting at the centroid. It has, let's take the x-axis, it has a distance of y, which is equal to 0.5 meters. And so due to this moment arm, well, this force will cause a bending moment around the x-axis, 800 kilonewton times 0.5 meter, that makes 400 kilonewton meters. So the same for the y-axis, as you see, this time the distance is x and the moment trying to bend around the y-axis can be calculated as 800 kilonewton times 0.25 meters, which makes 200 kilonewton meter. So due to this 800 kilonewton in our section ABCD, compression 800 kilonewton, bending mx 400 kilonewton meter, and another bending moment around y 200 kilonewton meter will be acting. Let's try to find the sigma values in points A, B, C, D. When we start with A, well, due to this normal force minus 800 compression, we will have a negative sigma, and due to mx, well, when we look at the section mx, well, the bending will be in this direction. So in the front surface, we will have positive, that means tensile stresses, so we will have plus. This is my bending moment. This is the distance from the neutral axis, 2.25, and this is the moment of inertia, which we have already calculated. Well, let's take the second bending moment, my. Well, this time, this is my axis. The bending will be in this direction, and again, in point A, we will have, when you bend like this, in point A, due to my, we will have again a positive tensile stress, and 200 times the distance from the neutral axis and divided by the moment of inertia. So, due to superposition, we will have a total of 9.88 kilopascal in point A. In this section, we don't have a shear force and no torque. That means we will not have any shear stresses. You can repeat the same for other points in sigma B. Well, in each point, the uniform distribution of the Normal stress due to that 800 will not change. Well, again, due to bending around X, a positive, and this time due to bending around Y, this time we will have a negative sigma in this wall. So this will be negative, and the result is 49.4. The point C, well, we will have a uniform distribution of the normal force due to the compression. So you see these are all negative. This time, due to bending around X, we will have a compression in C, and due to bending around Y, also compression. So my result will be minus 128. Point D minus 800 minus, and this time, well, point D will be in this point, and due to My, we will have a positive sigma, and the total is minus 69. When we draw the distribution, you see in point A, we will have a positive sigma. In all other corners, compression will be acting. Second problem, we have a bar, solid bar, diameter 40 millimeter. It is subjected to forces at its end. And the question is, well, in this solid bar, determine the stresses in point A. So let's put our axis. This is my X, Y, and Z axis. Well, the section we are interested is here. So let's cut through this section and put all possible internal forces and moments. Well, we may have a normal force, two shear force components. We may have a torsional moment, that means a torque, and we may have two components bending around Z and bending around Y. So we're going to determine these unknowns with the help of our equilibrium conditions. So, well, may look a little bit complicated, but if you go step by step, well, the problem is actually very simple to solve. Let's start with sigma fx. That is my axis. So we see that there are no forces besides n. So the forces 500 and 300 are not in the x direction. So the normal force is 0. That was the number 1. Sigma fy equals to 0. So my y-axis has 300 plus. You see, this is the positive direction of y. And we have also plus vy. So you see this result is now negative, which means the direction I have chosen in my drawing is not correct. The actual force Vy is in the opposite direction. So that was step number 2. The third, sigma Fz equals 0. This is my z-axis, and this is the Vz. And here we have minus 500, and this time Vz equals to 500. Okay, let's clear everything and go to the moments. Sigma mx, that is this value, this axis, and a moment around this axis would cause a torsion. As you see, well, these two forces are acting on this x-axis, so they don't have any torsion. So that means my torsion or my torque is zero. There is no external force which causes a torsion of this bar. Second one around y. Y is my axis and my force that 500 is trying to rotate around the y-axis, and it has a moment arm of 150 millimeters. And as you see, we have also my my value. So when you write down the equilibrium, my minus this value should be equal to 0, and you find that 75 Newton meter is the acting bending moment in the critical section. So positive and negative of the moments are well determined with the right hand rule. We all know that. Let's take the 500 newtons and you have the y-axis. You take your right hand and direct your thumb in this direction, and your other fingers will point in the positive direction. So as you see, well, this is my positive direction, and my 500 is creating a negative moment. And my my value, which I have drawn the direction, is positive. So let's do the same for the axis Z. Z is in this direction. So put your right hand over here, and these are the positive directions. And as you see, well, your 300 is trying to rotate in the other direction, so it will have a negative value, and my my value, sorry, my mz value, which I have drawn over here, is positive. So if you write down the equilibrium, you find that mz is 45 Newton meter. Well, and now you have the acting forces and the moments in the critical section. This is my section, and these are my forces. No normal force, no torque. At the beginning, we can calculate the area of the section, the moment of inertia, polar moment of inertia, and the Q values for shear, and then start with the calculation. Normal stresses in point A may be caused due to normal force and bending moments. The normal force is 0. This disappears. Well, bending around Z, well, it will look like this. And as you see in this case, the stress distribution will be like this. And my point A lies directly on the neutral axis. So this distance, this y, is 0, and this component disappears. Now, the last component is the bending around y. Well, around y. Well, it will cause a distribution like this. And as you see, well, this is my section. And in this section, I have a bending like this, bending around y like this. In this case, I have a positive tensile stress in point A. Well, the numerical value may be calculated. This is the moment. This is the distance, which is the radius, and that is my moment of inertia. And in point A, I have a normal stress of 11.9. Shear stresses. No shear stresses due to torsion. Torque is zero. Shear stresses are only due to shear forces. One force is acting in this direction, that is 300, and another one in the Z direction, that is 500, 500 and 300, these two forces. Let's start with the simple one, Z direction. So Z direction, we have that 500. In this case, the stress distribution due to shear force will be like this. It will be maximum in the middle. On the surfaces, the shear stress are zero. My point A lies on the surface, so the tau value on the surface is zero. You see tau x z. What does it mean? X means x is the direction of the normal of the section. Okay, this is my section. As you see, this is my section, and its normal is directed in the x, and the direction of the shear stress which we have calculated is in the z direction. So this is how the subscripts are taken, and this is for point A. Now let's clear everything and go to the other shear stress component. Well, it is 300. Well, this time the shear stress distribution will be like this. So in point A, it will be maximum, and we have to use this formula to do this calculation. We know the shear force, we know the moment of inertia, we know the thickness in this point, and we need to calculate the Q value. How do you calculate Q? If this is your point, you draw and shade this area. This area is 1 over 2 pi r square, and you find the centroid of this area, and the distance of the centroid from the neutral axis is y prime. And well, this is your y bar, which you can find in geometry books, and this is your a value. The calculation gives you 5333 and minus 6. And if you put all these values in, you find that your tau xy is minus 0.318. Okay, we can show the stress state on a volume element as sigma 11.9 and tau 0.318. Well, for shear stress calculation, you do not have to use this formula when you have, let's say, simple sections and you are interested in the maximum value of the shear stress in these sections. Well, for circular, the tau max value can be taken as 4 over 3 V over A is the area. For rectangular section, 1.5 V over A. So in our case, if you would take the formula and would put your V and A, you would end up with the same result and find the same value. Well, this type of calculation is much easier. Well, in this video, we have solved two combined loading conditions and made stress analysis and found the stress states in some points. Thank you for listening.